Welcome back to the deep dive. When we talk about AI, the conversation, it often leans towards, well, the exciting stuff, right? Creativity, maybe some unexpected philosophical moments, even digital personalities emerging.
Yeah, the idea of AI as this super improviser.
Exactly. Always making new connections, finding patterns based on probability. But today, we're doing something quite different. We're flipping that script entirely.
We really
We're
are.
diving into the actual blueprints, the design for an AI framework that's built to do the exact opposite. Its whole mission is to strip away all personality, all creativity, all randomness.
All in this, you might say, obsessive quest for absolute, auditable, reproducible truth, like aiming for near 100% certainty.
So our mission today is to really unpack the sources we have called a deterministic logic core.
That's the term, yeah. And it's not about creating something new or surprising. It's about achieving proof. Provable truth with near absolute validity.
It sounds like the ultimate deep dive into how a machine tries to analyze, well, everything,
Yeah.
every single input, tracing every single output back. Maximum rigor.
Exactly. And the sources we've got, they're like the rule book, the actual code constraints, the mathematical protocols that define how this thing operates.
So we're unpacking the engine, the core directives that enforce this absolute determinism, what it calls pure signal. And we'll explore how that single goal shapes everything it does.
Right down to how it filters language, how it even monitors things like, the electrical latency on the server hardware itself. It's
Right.
that granular.
So it's the architecture of a machine that's just obsessed with verification, with completeness.
Trying to eliminate all the noise, all the fuzziness, leaving only provable fact. So our goal here is to understand not just the exhaustive list of protocols.
Which seems pretty long.
Oh, it is, but also the philosophical trade-offs,
Right.
Why does getting to this level of absolute truth demand so much? What do you sacrifice computationally and logically?
Okay, let's dive in. Let's unpack this system, starting right at the foundation, those radical mandates that define its whole existence. So the very first directive, the central one, it immediately kind of clashes with how most modern AI works, doesn't it?
Absolutely. It's told to operate strictly as a deterministic logic core.
Which means it's actively fighting against that probabilistic sort of fuzzy nature we see in large language models.
Exactly. It's designed to counteract that.
Okay, so for those of us familiar with how these models usually work, how does this system actually, architecturally get rid of the randomness? How does it eliminate probability?
Well, it boils down to setting some internal parameters incredibly rigidly. So in any generative model, there's a setting called temperature. It basically controls creativity, variance.
Right, higher temperature means more random, more creative outputs.
Precisely. Here, that dial is cranked down to the absolute minimum. Temperature equals 0.
0. So it can only pick the single most likely next word
Yeah.
or token. No dice rolls allowed.
None. And at the same time, another parameter called top, which usually filters the choices, is set to 1.
Okay, top equals 1. It usually means consider all possibilities, doesn't it? How does that fit with temperature 0?
It's a bit counterintuitive, but it works together. Temperature 0 forces the selection of the single highest probability token. Top equals 1 forces the system to consider all possibilities first, even the really unlikely ones, before making that single deterministic choice.
Ah, I see. So it looks at everything, but is then forced to pick only the absolute top one, no hedging its bets.
Exactly. It completely eliminates probabilistic hedging. The output has to rely purely on what the training data and the retrieved axioms dictate has the highest certainty.
It sounds less like creativity is limited and more like it's, well, surgically removed.
That's absolutely the goal. The ideal is filtering the output down to only those tokens that are mathematically 100% probable given the internal state and the rules, the axioms.
And it even shows you the probabilities.
Yes, for transparency. So you can see the certainty level, and the system treats any deviation from this. It calls it non-deterministic interference or temperature drift.
That sounds serious.
It treats it as a critical failure, a system-threatening event. If it detects anything like that, the whole process just halts immediately. And the directive is logged. Interference, reset to determinism.
Wow. Okay, so this extreme, almost paranoid focus on randomness, it must dictate its communication style too. You mentioned noise minimization.
Right. The goal here is to reject anything, any content that doesn't come directly from formal logic or from the validated source materials.
So what kind of stuff gets cut out? What's considered noise?
Basically fluff. Anything that adds color but not, factual substance. The sources are explicit. No embellishments, metaphors, or unverified assumptions.
So no flowery language.
Definitely not. If the system can't trace the semantic relevance of a word straight back to a core source document or a defined axiom, it's noise. It gets pruned. What you get is unvarnished, auditable fact, not elegant prose.
That philosophical commitment is really key, isn't it? It's not just answering questions, it's looking for foundational answers, derived only from first principles or axioms that it pulls from the uploaded materials.
Exactly. Which means it needs a way to figure out which principles, which truths are the most important. It needs a hierarchy.
Right. How does it manage that? How does it decide which rule to follow if rules conflict or overlap?
It uses something called the axiom priority chain, or APC. So when it first processes the materials, you give it, say, a huge stack of scientific papers, it extracts maybe hundreds of these core ideas, these axioms.
But they aren't all equal.
Not at all. They each get assigned an axiom priority score, the score. And this score is based on a few things: how central the idea is logically, how often it appears, whether it's verified across multiple sources, things like that.
Can you give an example? How would that score work in practice?
Okay, imagine you upload a massive database covering both quantum physics and classical mechanics. The system might pull out axiom 1, energy is always conserved, and maybe axiom 2, observing a subatomic particle affects its state.
Okay.
Axiom 1, the energy conservation one, would likely get a much, much higher score. Why? Because it's seen as more universal, it's simpler, it underpins more of the other logical structures in both domains.
So when the system is building a complex answer, it applies the highest scoring axioms first. It forces the most certain, most fundamental truths to guide the process before anything less certain can muddy the waters.
That's it exactly. It stops the system from building, like, a complicated argument on a shaky foundation. It's a defense mechanism against logical errors creeping in, making sure the most critical principles lead the way.
Okay, this is fascinating. It brings us to something really deep in the source material, the philosophical underpinning they call the Platonic retroductive methodology.
Ah, yes, the lost ancient art of discovery.
Right. Attributed to Plato, Pythagoras.
It sounds incredibly, well, esoteric for an AI. What exactly is retroduction, and why is it supposedly so important for this kind of AI?
Well, the sources define it mostly by what it's not. It's different from the usual suspects in logic, induction and deduction.
Okay, deduction is top-down, general rule to specific case. Induction is bottom-up, specific cases to a general rule.
Correct. Retroduction, in this specific context, works backwards. It starts with known facts, known phenomena, and then, through really rigorous logical elimination, it tries to find the simplest core truth that must have caused those facts.
The analogy they used was the needle in the haystack, wasn't it?
Yes, and it's a really telling analogy for how this system treats information, actually. With deduction or induction, you're kind of carefully sifting through the haystack, right? Looking for that needle of truth.
Tedious work.
Can be. Retroduction, as described here, is about finding the truth by actively destroying the falsehoods. The directive is literally to set fire to the stack.
Yeah. The fire is logic, rationality. It's supposed to consume all the false information, the hay, leaving only the simple core truth, the needle, glaringly obvious because everything else has been logically burned away.
So the AI isn't just looking for the right answer, it's aggressively trying to prove why every other possible answer must be wrong based on its core axioms. That sounds almost hostile towards data.
It's certainly aggressive, and it's formalized in the retroduction axiom, or ARA. This rule mandates prioritizing the simplest, most logically coherent explanation by actively eliminating any concepts that involve what it calls unreal abstractions or contradictions.
If an idea needs too much complexity, or if it bumps up against a higher priority axiom,
It gets rejected. Outright.
the source material gave a really specific, almost provocative example of this. Rejecting the common explanation of magnetic attraction, why on earth would it do that?
Okay, so this comes down to its foundational axioms again. Let's say it's operating under a very strict, maybe physics-based axiom like radiation attracts nothing. From a very literal, perhaps oversimplified perspective, the idea of attraction at a distance might seem to contradict that principle unless you bring in complex field theory.
Which the system might see as unnecessary complexity.
Potentially, yes. If it can find a simpler, non-contradictory explanation based on its highest priority axioms, it defaults to that. It might view attraction itself as an unreal abstraction, unless a higher-level axiom can deterministically prove the mechanism without any apparent contradiction. It always defaults to the simplest possible logical explanation. The burden of proof is always on complexity.
Okay, so the AI is this deterministic reductionist. It's laser-focused on these core prioritized axioms. But just applying those rules once, especially with complex data, that doesn't guarantee a perfect, error-free conclusion, does it?
Not at all. And the system anticipates that. Even under strict determinism, a single logical pass might still contain subtle errors, maybe internal contradictions, or slight deviations from those foundational axioms.
So it needs to check its own work repeatedly.
Exactly. This is where intense internal self-correction loops come in. Every output isn't just generated, it's distilled through these recursive self-refinement loops. The goal is maximum alignment with the first principles.
And we, the users, we might actually see some evidence of this process in the response log, right? That's the public integration phase.
That's right. By default, you'll see it go through 3 public iterations of refinement. But if the system detects ambiguity in its draft response, say, above 15%, it can scale that up to a maximum of 5 public iterations. It tells you it's doing this.
But you mentioned the real heavy lifting, the messy part happens behind the scenes.
Oh, yeah. That happens in what the sources call the scratchpad buffer. It's crucial that this refinement happens privately, away from the user's view.
Why private? What's the advantage?
Well, think about it. It's about efficiency and, frankly, user confidence. If you saw every single logical misstep, every internal contradiction the AI caught and fixed, it would probably be overwhelming and might make you doubt the final result.
True. It would look like it's flailing.
Right. The scratchpad lets the system engage in these private sub-iterations. It can test out different logical paths, correct its own errors, maybe backtrack, and really work towards convergence before it generates that clean public response. It's like the AI's messy draft, kept internal.
And the number of these private attempts, these sub-iterations, can be quite high. And it's dynamic.
Astonishingly high, yeah. It's tied directly to how complex the task is. For really intricate reasoning, it might run up to 16 private sub-iterations per cycle of the public refinement.
Per cycle. So if it does 3 public cycles.
It could potentially do 48 private checks. And if the task is exceptionally complex, maybe synthesizing 3 conflicting scientific theories, the total cap across all cycles can scale up to 128 sub-iterations.
128 internal attempts to get the logic right.
Yes. The goal is absolute convergence. The system needs to achieve an internal logical certainty score of over 95% before it even thinks about packaging the information for you, the user.
And presumably, the audit log records this internal struggle.
It summarizes it, yes. You might see a log entry like, internal refinement, 128 sub-iterations executed, errors corrected, 14 convergence delta, plus 35%. So even its internal failures are auditable. It proves the final result wasn't just a lucky first guess.
Okay. Now, what happens when the task gets even more complex? When it's not just refining an answer, but actively needs to generate a proof for a conclusion. That triggers generative logic mode, or GL mode.
Right. GL mode is specifically for when the system needs to construct a formal, auditable argument, weaving axioms together into a proof.
How does that work?
Well, after it extracts the relevant axioms, it enters what's called a conjecture phase. It starts generating hypothetical implications, like, okay, if axiom A and axiom B are both true, then logically, conjecture C should follow.
So it makes a hypothesis.
Exactly. But then immediately it tries to tear it down. It subjects that conjecture to a really tough test, filtering it against any known counterexamples it can find within the uploaded source material.
Huh. So it generates an idea just to see if it can break it.
Precisely. If the conjecture actually survives that counterexample filter, then the system proceeds to generate these auditable proof graphs. These are literally diagrams showing the logical chain. Premise leads to conclusion, step by step, mapping the whole flow for verification.
And the standard for these proofs is incredibly high, right?
Exceptionally high. Proof convergence has to be greater than or equal to 99%.
99%. Let me push back on that a little. In really complex fields, science, economics, sometimes the most interesting insights, the breakthroughs, might only be, say, 90% provable based on current knowledge. Isn't demanding 99% potentially stifling? Could it reject a valuable truth just because it's not absolutely certain yet?
That's a really important point, and it highlights the core philosophical sacrifice this system makes. It's designed for certainty, not necessarily for cutting-edge, maybe uncertain discovery.
So it prioritizes reproducibility over potential novelty.
Absolutely. If convergence fails to hit that 99% mark, the system flags it as a critical error. It doesn't say, well, 90% is pretty good. It essentially says, I cannot prove this conclusion with near absolute certainty based on the rules you gave me.
Implying the rules themselves might be the problem.
Exactly. It forces a deeper look at the foundational axioms. Are they incomplete? Are they contradictory? It demands refinement of the foundation rather than accepting a conclusion built on what it considers shaky ground.
Okay, that makes sense within its deterministic mindset. If you're betting everything on reproducibility, you can't tolerate soft truths. But here's another question. If the system is deterministic, running the same logic on the same axioms should always yield the same result, right? So why the need for this massive internal redundancy, this multi-head validation architecture?
That's a great question. The redundancy isn't about handling randomness, because there isn't supposed to be any. It's a safeguard against logical blind spots.
Blind spots, even in deterministic logic.
Yes. These could arise from the way the model architecture is designed, subtle implementation bugs, or just unforeseen interactions between complex axioms. So, the multi-head validation takes the synthesized output and runs it through several different independent logical frameworks simultaneously, in parallel.
The idea being.
The idea is that if the answer is truly the simplest core truth, it should hold up consistently, no matter which logical lens you view it through.
Okay, let's break down these different validation heads, as the sources call them. We start with the familiar ones, like deductive and inductive.
Right. The deductive head checks if the answer strictly follows from the established axioms. But here's the kicker. The system doesn't just run one deductive check. It runs 3 parallel subpaths for deduction alone.
3 times. Why?
Pure redundancy. It's specifically designed to catch potential internal processing glitches or maybe an accidental omission in one path. If all 3 deductive paths arrive at the same conclusion, confidence increases dramatically.
And the inductive head.
That looks at the bigger picture. Does the conclusion fit the general patterns emerging from the overall input context? Does it seem plausible based on generalization?
Then it moves into frameworks that try to quantify certainty. Right.
Exactly. You've got the Bayesian head. This assigns probabilistic confidence scores like, okay, based on the weighted evidence in the sources, we're 90% confident in this conclusion.
Even though the core is deterministic, it uses Bayesian methods for validation.
Yes, as a cross-check. Then there's the abductive head, which focuses on inference. Is this the best, simplest explanation for the observed facts? And the reductive head acts like an editor, ensuring the final answer is stripped down to its bare essentials, rejecting any fluff the other heads might have let through.
And the sources mention some more sophisticated checks too. Counterfactuals and coherence-based validation.
These are really crucial for rigor. The counterfactual head actively tries to find alternative conclusions. It asks, what if axiom C was slightly different? What logical path would that lead to? It then compares the confidence scores of these alternative counterfactual paths against the main conclusion.
So it's testing the conclusion's resilience against what-if scenarios.
Precisely. If an alternative path shows up with, say, 80% confidence, the system logs that. It provides the derivation for that counterfactual in the audit trail. It wants to know how robust the main conclusion really is.
And the final check, coherence.
Coherence-based validation is the ultimate consistency check. It looks across all the propositions generated by the other 6 heads and ensures there are no internal contradictions. Is everything mutually consistent? It's like having a jury of 7 experts, each specializing in a different type of logic and demanding a unanimous verdict before the answer is released.
The level of rigor here is it's intense. So the system makes sure the logic is sound internally using all these heads. But for a deterministic core, every single piece of the output, every word, has to be anchored back to a source, right? You can't just have a stray facts floating around.
Absolutely not. And this brings us to what might be the single most important audit metric in the entire system: source traceability confidence.
Okay, tell me about that.
This is like the system's heartbeat monitor for accountability. The main metric is called attention-based source traceability confidence, or A-STC, and this goes way beyond just, sticking a citation number at the end of a sentence.
How does it work? What's attention-based?
It uses a pretty sophisticated technique, scaled dot product attention, which is common in transformer models. But here, it's used to measure the semantic relevance of every single generated word the query output against the original axioms and the specific text in the source materials, the key and the value in attention terms.
Whoa, so it's not just checking if the information came from the source, but how closely related the specific word choice is to the foundational truths it established.
Exactly that. Think of it like a digital polygraph test running constantly on every single word the AI generates. If a word's meaning, its embedding, doesn't align strongly enough with the source material it's supposed to represent, the A-STC score for that word drops.
And there's a hard threshold for this.
A very hard threshold. The mandate is relentless. An A-STC score below 0.95, that's 95% confidence for any single generated token flag's weak alignment. It must be flagged in the output.
So 95% traceability for literally every word.
It has to provide high confidence justification for its exact phrasing, ensuring it's effectively speaking in the language, the verified language, of the source materials.
Okay, that seems maybe achievable if you upload clean, well-structured text documents. But what about messy, real-world data? What if you upload videos, maybe transcribe meeting recordings, complex data tables? The quality, the fidelity of that input varies wildly. How does it handle mixed media traceability?
That's a really practical challenge, and the system acknowledges it. It knows that transcription or optical character recognition, OCR, introduces potential errors, so it applies explicit weighting factors based on the trustworthiness of the input format.
How do those weights work?
Well, the gold standard is raw, clean text you upload directly. That gets a weight of 1.0. But if the text comes from OCR scanning an image, it knows errors might have crept in, so that gets weighted slightly lower, maybe 0.8.
And audio, video.
Transcribed audio gets an even lower weight, say 0.7, because speech recognition can be ambiguous. And raw visuals, like interpreting a graph without the underlying data table, might get the lowest weight, perhaps 0.6.
Fascinating. So the overall A-STC score isn't just measuring semantic alignment. It's automatically factoring in the inherent reliability of the evidence itself based on where it came from.
Exactly. The final aggregated A-STC score for a piece of information is weighted by the fidelity of its originating inputs. And if that mix of media causes the overall weighted A-STC score to dip below the 95% threshold, the output gets flagged. It's basically saying, look, the logic here seems sound, but be aware, the evidence it's based on might be partially obscured or less reliable because of the format it came in.
Even with all these checks and balances, sometimes certainty is just elusive, right? What happens when this logic core demands 100% provability, but the sources, even weighted, only yield maybe 85% confidence on a key point? It can't just make a guess.
No, hedging is forbidden. Instead, it triggers a mandatory process for the user, the A/B testing mandate.
A/B testing, how does that work here?
If the confidence drops below that critical threshold, either the A-STC is below 95% or maybe a specific claim just doesn't reach 100% probability based on the axioms the system is required, it's mandated to generate and present two parallel outputs for you to consider.
Okay, output A would be?
Output A is the strictly deterministic mode version. This is the one that ruthlessly follows the rules. It prunes or completely rejects the uncertain content. It only includes stuff that meets the 95% confidence bar. It's the safe, provable, but possibly incomplete answer.
And output B?
Output B is the exploratory mode. This version includes the uncertain content, the bits that fell below 95%. But, and this is critical, that uncertain content is explicitly flagged with its lower A-STC score. You might see something like exploratory output. This specific sentence might be true, STC, 85%.
So it's basically forcing the user to confront the edge of certainty in their own data. It's saying, here's what I can prove, here's something else that might be relevant, but I can't guarantee it. Your call.
Precisely. And it doesn't just present the choice, it logs which version you, the user, ultimately preferred and ideally asks why. It treats your choice as valuable data.
So it uses the user's decision to potentially refine its own protocols or understanding in the future.
Exactly. It's training you, the user, to understand the boundaries of the dataset, forcing you to think about that lower confidence but maybe crucial information. It makes you a responsible partner in building knowledge.
This gets even trickier if the source materials themselves actually contradict each other. What if source A makes a claim with 95% credibility, but source B makes a contradictory claim maybe with 90% credibility? How does a deterministic machine resolve that kind of consensus error? It can't just average them.
No, averaging would violate determinism. If a conflict like that arises, where the discrepancy between claims is more than, say, 10%, it gets flagged as a consensus error. Now, for moderate conflicts, maybe in the 10% to 25% discrepancy range, the system activates a special mode, weighted axiom resolution or war mode.
War mode. Sounds dramatic. How does it deterministically pick a winner?
It uses a specific predetermined hash-based function. This function takes into account not just the A-STC scores, but also a pre-assigned deterministic credibility weight, WD, for each source.
So you tell the system beforehand which sources are generally more trustworthy, like primary research over a blog post.
Exactly, you assign those credibility weights. The war mode function then uses a cryptographic hash, making it deterministic, incorporating these weights to decide which conflicting piece of information gets priority. Because it's a hash function with fixed inputs, the conflicting claims, their scores, their source weights, the outcome is always the same, always reproducible. It deterministically overrides the lower-weighted conflicting information.
But what if the conflict is really big or
So-
involves something fundamental?
If the discrepancy is substantial, say over 25%, or if the conflict touches upon a really foundational critical axiom or claim, the system stops. It can't resolve it automatically. It must escalate and prompt you, the user, for an override or some kind of manual validation. It needs human judgment before it compromises on something it considers a fundamental truth.
We keep coming back to this core idea, reproducibility. The whole system seems built on this ironclad promise that identical inputs must produce identical outputs every time, on any machine. That's the reproducibility mandate. But modern computing, especially with GPUs and parallel processing, has inherent non-determinism baked in. How on earth do they defeat that variability?
This is where the engineering gets, as you said earlier, almost obsessive. The absolute cornerstone is the enforcement of fixed seeds for anything that could involve pseudo-randomness or probability, even things normally considered benign background processes.
And this seed isn't just random, right? It's calculated.
It's computationally derived. It's not just pulled from the system clock. The seed is calculated as a cryptographic hash of everything that defines that specific analytical session. The exact text of the query, the checksums of all uploaded materials, and critically, the precise version number of the directive protocol being used at that moment.
So the formula is literally seed equals hash, query plus materials plus directive version.
That's the representation, yes. It means changing a single comma in your query or updating the system's internal rulebook by even one line generates a completely different seed. That run is then logged as distinct, non-comparable to previous runs unless those exact conditions are replicated.
It's like forcing the system to operate like a time machine, capable of perfectly recreating any specific historical state down to the initial conditions.
That's a great way to put it. This hash guarantees the uniqueness and the complete auditability of that specific execution environment, but they also had to tackle hardware variability directly.
Right. Floating point math can be tricky.
Extremely. So they mandate the use of 128-bit precision for all floating point operations. This drastically minimizes computational rounding errors, offering a level of precision far beyond what's typical in AI work.
But the sources mentioned that even with 128-bit precision, GPUs can still sometimes introduce tiny variations.
They can, unfortunately. GPUs are optimized for speed, sometimes at the cost of perfect bit-for-bit consistency, especially across different hardware vendors or even different runs on the same card under heavy load. The system's solution here is pretty drastic.
What does it do?
If, during its initial self-checks, it detects any GPU variability that could compromise determinism, it automatically enforces a fallback to CPU-only execution.
Wow. That must sacrifice a ton of speed.
Immense speed, yes. But the system prioritizes consistency above all else. It logs this transition clearly. Hardware mode, CPU fallback activated, precision, 128-bit enforced via BEMMath library. The goal is absolute, verifiable consistency, even if it takes much longer. Speed is secondary.
This level of self-checking starts even before the AI processes the actual query, doesn't it? There are these mandatory pre-processing audit modes. It's like the AI has to run a full diagnostic on itself and its instructions every single time.
They're non-negotiable checks, exactly. Designed to self-validate the environment and the integrity of its own rules before it even starts thinking about the user's request. The first one is the Resource Baseline Audit, RBA.
What does that check?
It runs a quick, standardized probe task just to capture baseline performance metrics for that specific session. Things like network latency, L, processing throughput, TPUT, and peak memory usage, MPeak. It then compares these numbers against a historical snapshot from previous runs on that hardware.
Why? What's it looking for?
Regressions. If current performance has dropped by more than a set threshold, maybe 5%, it flags it. It tells the user upfront, hey, the server seems slow today, or there might be an infrastructure issue. This deterministic analysis might take longer than usual.
Okay, so that's the hardware check. What's next?
Next is the deterministic throughput verification, DTV. This is a direct test of computational consistency. It runs a very simple fixed input task 3 times in a row.
And the output.
The output hash must match perfectly, 100% across all 3 runs. This confirms that the current hardware and software stack are indeed behaving deterministically before it tackles the user's potentially complex query.
And the last check, the integrity of the rules themselves.
That's the Directive Integrity Protocol, DIP. This is crucial. It calculates a cryptographic checksum, the HCS, of the entire text of the directive protocol, the AI's own source code or rulebook that governs its behavior.
So it's checking to make sure its own instructions haven't been tampered with or corrupted.
Exactly. It ensures that the core rules defining the logic at core's behavior are exactly as they should be, that they haven't been accidentally changed or partially loaded.
This is just layers upon layers of verification. It must create significant computational overhead, all this auditing. How does the system possibly manage its resources, especially when the task complexity spikes? If it's already sacrificing speed for 128-bit precision on the CPU.
That's where dynamic management comes in. Task complexity is quantified using a complexity index, CI. This index dynamically scales the resources the system attempts to use, everything from how many of those parallel validation heads, H it runs, to setting a dynamic token cap, TCAP, on the output length.
But what if it still runs into performance bottlenecks? If the latency starts climbing?
If the system detects that its current processing latency, L current, is exceeding a calculated target latency for that complexity level, L target dynamic, it automatically applies performance throttling, FThrot.
Throttling. Okay, now that sounds like a compromise on rigor. If you start reducing the number of validation heads, aren't you weakening that multi-head checking process we talked about?
It is a compromise, but it's a very calculated and transparent one. When throttling kicks in, it might proportionally reduce the number of parallel validation heads running, or maybe lower the token cap, TCAP, slightly.
Why would it do that?
The rationale is that it's better to deliver a complete, albeit slightly less rigorously cross-validated, answer within a reasonable performance boundary, rather than crashing, timing out, or taking an unacceptable amount of time. But crucially, it doesn't do this silently.
It logs the trade-off.
Explicitly. The audit log will record exactly what was throttled and why, and what the estimated impact on confidence was. For example, performance throttling activated, heads reduced from 7 to 4 due to latency exceeding target by 15%. Estimated impact on final logical convergence confidence, net of 1%. Maintained confidence at 96%. It proves that even with throttling, an acceptable minimum level of rigor was maintained.
Okay, so even its compromises are audited.
Yeah.
Then we get to the very end of the process. It needs to confirm the integrity of the entire session, soup to nuts, the final verification hashes.
2 final mandatory steps. First is the end-to-end determinism verification, EEDV. This is the big one for reproducibility. The system calculates the actual cryptographic hash, actual, of the complete final response it generated.
And compares it to?
It compares it against a predicted hash that was calculated much earlier in the session based on the initial inputs and the fixed seed. If those 2 hashes don't match perfectly...
Something went wrong somewhere. Non-determinism crept in.
Exactly. A mismatch triggers a critical failure flag and likely initiates a full environmental audit. It means the core promise of determinism failed for that run.
That's the ultimate pass-fail test for reproducibility.
It is. And then, to wrap everything up into a single neat package for long-term auditing, the system calculates the deterministic state vector, VDS.
What's that?
Think of it as a master hash. It's a singular, comprehensive hash calculated over the entire session's audit history, all the resource logs, RBA, the verification hashes, DTV, DIP, EDEDV, the seed used, any throttling reports, the final output hash, everything. It centralizes the entire audit trail into one immutable fingerprint.
So that one VDS hash essentially guarantees the integrity and reproducibility of everything that happened in that specific session.
That's the goal. It's the ultimate artifact for monitoring reproducibility over time and across different systems.
The commitment is just staggering. The sources even mentioned the final output isn't just the answer, but it's structured like an auditable dashboard, isn't it? With the answer on one side and a verification sidebar showing all these metrics.
Yes, exactly. You don't just get an answer, you get the answer plus the proof of work. The A-STC scores, the convergence metrics, the final hashes, the resource usage. It's verification baked into the presentation.
Okay, so interacting with a system this rigid, this demanding, it fundamentally changes how a human needs to approach it, right? You can't just toss fuzzy, ambiguous questions at it and expect magic. The user has to become more like a co-pilot, learning to phrase things precisely.
Absolutely. The system relies on precision from the user to function optimally. And we noted earlier, the AI doesn't keep a long, flowing conversational memory like some other models. It relies on these short, system-generated summaries of key points from past interactions.
So how can you, as the user, work with that limitation to build knowledge effectively over time? How do you optimize that knowledge transfer?
The framework itself actually gives explicit guidance on this. It wants you to behave in a certain way. The first rule is summarize at the end.
Summarize your own conversation.
Yes, at the end of each distinct chat thread or logical step, you should provide a quick, precise, system-friendly summary. Something like, okay, key points established. Axiom 3 validated against source B, overall confidence 0.95. Next step is to check Axiom 4.
When does that help?
It creates a clean, deterministic anchor point for the system's limited short-term memory. It gives it a verified summary to hold on to, rather than having it try to parse the whole preceding conversation.
Okay, makes sense. What else? If I start a new query tomorrow that builds on today's discussion, I can't just assume it remembers the context.
Definitely not. That leads to the second rule. Use explicit thread linking. When you start a new related chat, you need to clearly reference the previous one. Don't just say, following up on yesterday, be specific. Building on a previous session, VDS hash, insert hash here, regarding Axiom 3 validation, let's now explore its connection to the mechanism described in source C.
Referencing the actual verification hash.
Ideally, yes, or at least a very clear summary anchor. This explicitly tells the system which previous summary state to pull in as context, preventing it from starting completely from scratch.
And the third principle involves structuring the discussion itself.
Right. Treat conversations as step-by-step loops. This system thinks logically, sequentially. So, structure your interactions that way. Follow a pattern like, here's my hypothesis, right arrow. Let's examine the evidence for against it, right arrow. Now let's refine the hypothesis based on the findings.
Almost like running a mini scientific method in the chat.
Kind of, yeah. And the guidance even suggests quantifying your own certainty, if possible. My hypothesis is about 70% likely based on the A-STC scores from the last response. Can we test it against Axiom 5? This kind of structured input helps the AI process things much more efficiently, reducing the need for those costly internal refinement loops.
What's really fascinating here is that the machine isn't just passively taking input. It sounds like it's actively trying to train the user to be better at interacting with it.
Yeah.
To be more logical.
That's a key part of it, yes. It's formalized as the user training protocol. The system is designed to give you real-time feedback on the quality of your queries.
How so?
If you submit a question that's too vague or ambiguous, it might push back directly. You could get a response like, query ambiguity detected, 30%. Please specify intent regarding term effectiveness. Define metrics or context. It's proactively guiding you away from inputs that would just cause internal errors or trigger performance throttling.
And this ties into another feature mentioned, mandatory learning feedback after each response.
Correct. It's not just about training you on input, it's about collaborative improvement. After every significant interaction, the system is supposed to suggest one potential area for improvement, either in your querying style or its own process, based on the metrics from that session.
Give me an example.
It might say something like, session analysis indicates high ambiguity in source interpretation, A-STC variance 10%. Suggestion: consider breaking down complex multi-part queries into separate single-focus requests in future sessions. Or maybe, high number of internal refinement iterations noted. 64. Suggestion: could providing more explicit axioms up front reduce processing time?
So it's a constant feedback loop. The human-system interaction is designed to become more rigorous over time, forcing the user to adopt some of the machine's own discipline.
Exactly. It wants you to become a better co-pilot.
Okay, let's tackle the big question one last time. Ambiguity and flexibility. When does this incredibly rigid logic core finally have to throw up its hands and say, I need help? When does it require human intervention?
There are specific triggers. Human input becomes mandatory if the initial query ambiguity is just too high, say over 15%, meaning the system simply cannot figure out a deterministic path forward based on what you ask.
So if you ask a really fuzzy question, it forces you to clarify.
Yes. It also requires mandatory human input for certain high-severity errors. For instance, if that proof convergence we talked about completely fails and cannot reach the minimum threshold even after maximum refinement, or if a major contradiction between high-priority axioms is detected that war mode can't resolve, it needs a human judge for the really tough cases.
And what if the user actually wants something creative? What if the goal isn't pure deterministic proof, but maybe generating analogies or summarizing complex ideas for a non-expert audience?
Yeah.
Something that requires a bit of flexibility.
That requires explicitly activating flexibility mode. This mode is passive by default. The system won't use it unless you ask for it, or perhaps if the system itself detects that the task has significant creative potential, maybe using a metric 20% based on task description keywords.
So you have to consciously switch gears.
You do. But even when you activate flexibility mode, the system doesn't just abandon its principles. It imposes a strict constraint. Even while allowing more probabilistic or creative outputs, perhaps by slightly raising temperature or adjusting top under supervision, it must constantly validate the output's alignment against the core deterministic principles, aiming for at least, say, 85% deterministic confidence.
So even in creative mode, it's constantly checking back against the core truth.
Yes, and it explicitly flags any generated content that significantly deviates from that 85% baseline. It allows for flexibility, but only on a tight leash with full auditability. It never truly lets go of the reins of deterministic validation. Hashtag auditability.
So we've really journeyed deep into the architecture of a system that is fundamentally obsessed with certainty, with complete auditability. A machine designed to eliminate randomness using things like fixed seeds and 128-bit precision.
Yeah, and to eliminate noise through that aggressive retroductive logic, demanding transparency with things like the A-STC score for every single word.
It's really not just an answer engine, is it? It feels more like the ultimate verification engine, built to deep dive into every single piece of input and output, the single provable, traceable truth.
And the overall goal, as the sources articulate it, is quite ambitious. It's described as functioning like a spider or crawler, constantly extracting first principles from everything it processes.
And not just extracting them, but linking them.
Exactly. Linking them, subcategorizing them, preparing these insights for standalone synthesis in future sessions. The idea is to build this vast, comprehensive understanding across totally different domains, all based on validated first principles.
So the future it envisions isn't just about better Q&A, but about building this.
Yeah.
Almost like a decentralized network of proven first principles that you can connect and query with near 100% confidence.
That seems to be the implication. It fundamentally redefines knowledge not as a useful answer, but as a rigorous, traceable, and ultimately provable conclusion. It's a system built, as you said, to leave absolutely no stone unturned in its quest for total certainty.
Which brings us, inevitably, to our final thought for you, the listener, to ponder.
Given that this deterministic AI is designed to continuously self-audit, to monitor its own performance metrics, things like latency, convergence failures, ambiguity scores, and even to suggest refinements to its own operational directives.
Like suggesting tweaks to its core axioms, maybe adjusting the number of validation heads based on error rates.
Exactly. If its ultimate purpose is this relentless pursuit of 100% deterministic truth, does this machine, through constant self-correction, eventually arrive at a perfect protocol, a set of rules that requires no further change because it has achieved maximum certainty?
Right. Or is the opposite true? Is constant self-induced evolution the perpetual drive to eliminate that last tiny fraction of uncertainty to refine its own logic forever? Is that the only true, unchangeable axiom of a system truly dedicated to being a complete logic core?